Hello everyone and good afternoon. Thanks for coming to this talk. My name is Siva Chandra Reddy. Today I'm here to talk about the challenges of implementing the C standard library in C++. So before I start with the main talk, a few items here. First of all, who am I? I'm a software engineer at Google. I've been working on LLVM's libc project for the last 3.5 years. I was the main author of some of the core infrastructure pieces of this libc. I wrote the file-related infrastructure, I wrote the first Linux threading library, and I also wrote some of the initial parts of the math library. The outline for the talk is as follows. To begin with, as if my audience doesn't know what a C standard library is, I'm still going to explain what exactly is a C standard library. Next, I will present a short overview of LLVM's implementation of the C standard library. This talk is a result of our work towards building this LLVM's libc, this LLVM's C standard library. So I believe that having a good overview or understanding of the principles and the design goals of LLVM's libc will set up the context for the rest of the talk nicely. Next, I'll move on to the actual core part of this talk, which is the challenges we faced in building LLVM's libc and the solutions we employed to overcome those challenges. Throughout the talk, if you have any questions, feel free to interrupt me, raise your hands and interrupt me. I'll be happy to take your questions and answer them. If I'm unable to answer them, I'm happy to follow up with you offline after the talk. A few other general points. I'm going to show a lot of code snippets, but in no way do I intend this talk, or those code snippets and this talk, to serve as a tutorial on some C++ features. I'm going to show them anyway to illustrate the problem space we are faced with and also to make a case for the solutions we have employed to overcome the challenges. And also, some of the items I'm going to show you are actually anti-patents. I don't want you to walk away from this talk thinking that you could do the same thing in your projects. No, libc is a very special project. So we have that liberty to use those anti-patents, and so we have done them, and I will demonstrate and talk more about those anti-patents. All right, so what is the C standard library? As the name says, it is an implementation of the C standard library. That is the standard library specified by the C programming language standard. It is usually referred to as the libc. But a libc typically consists of much more than just the implementation of the C standard library API. At a minimum, it includes the runtime support system, which facilitates and enables this API. Think the file API, the thread API, or even the @exit function, for example. All of these pieces need to have certain data structures set up when the application starts. And the implementation of these API features make use of those data structures during program runtime. And when the application shuts down, the C runtime support system goes up and cleans up those data structures. Not only that, if you consider functions like @exit, this C runtime support system also calls the @exit callbacks at program shutdown time. So, at a minimum, the C standard library or the libc consists of the implementation of the C standard library API and the runtime support system which enables and facilitates that API. Few platforms like Linux cram a lot more into the libc. We have POSIX extensions, GNU extensions, and Linux extensions. pthread library is a POSIX extension. glibc provides a lot of convenience extensions. For example, the sign cost function from math.h. Likewise, glibc also provides a lot of Linux extensions, which are essentially syscall wrappers. The idea behind glibc providing those syscall wrappers is that glibc tries to provide a uniform interface, hiding the variances in the syscall ABI across various Linux versions. All right, so with that understanding of what exactly is a libc, let's talk about LLVM's libc. So LLVM's libc is an implementation of the C standard library. It's a greenfield libc implementation in the sense that we have started from scratch. We didn't copy code or we didn't inherit code from anywhere. We started from absolute zero. The aim is that eventually it can become a drop-in replacement for the legacy libc systems on any platform. For example, on Linux, we hope that sometime soon it'll be wide enough, large enough, big enough to serve as a drop-in replacement for glibc. The interesting aspect of LLVM's libc for this talk and for this conference is that it's implemented in C++. Our aim and goal is to make the implementation, the source code, look and feel like that of a modern C++ library. So the natural question that you might have is like, why did you choose C++? There are a few obvious reasons, very trivial, simple reasons. C++ has RAII. C++ has templates. I mean, this is over C, right? I'm comparing C++ with C here. So in comparison to C, we have RAII, templates, the easy things that you can, the things which are obvious as to why we should pick C++. But there are more modern and powerful features like const expression, variadic templates, and maybe even concepts in sometime in future when we are able to use C++20 compilers. Concepts will help us formalize some of the internal abstracts, which are abstract interfaces that we have set up. Beyond using C++ as the language of implementation for LLVM's libc, we have a few other rules and goals also for LLVM's libc. One of the hard rule that we apply on ourselves as developers of the libc is to not include or handcraft any assembly language files in the libc source code. Couple of straightforward reasons why we do this. We want the entire libc source code to be instrumentable by sanitizers. Likewise, we want the entire libc source code to be static analysis friendly. There is an ulterior motive also behind having this hard rule. Like being part of the LLVM project, we would rather improve the compiler to do the right code gen for the target rather than use assembly language as shortcuts to write the optimum or optimized code. Most libc implementations like glibc and others have assembly language, handcrafted assembly language files, essentially for that reason, because they feel that by handwriting the assembly language files, they can provide the best optimization for the target, architecture. So one consequence of having this hard rule is that we cannot implement functions like setJump and logjump. These are functions from the C standard library. And you can't implement them in a straightforward manner in a high-level programming language like C++. So for such functions, what we do is drop down to using inline assembly. The worst we can do is use inline assembly. So I'm going to show the ugliest function in our LLVM's libc, which is the implementation of longjump. Well, setJump is also equally ugly, but similar kind. So this is a longjump implementation for x86-64. As you can see, it's mostly inline assembly. There is one line in the middle, which is not inline assembly, but everything else is inline assembly. The beauty of this, or the ugly thing about this, is that LLVM's libc is the only libc which does it this way. Everybody else have handcrafted assembly files for longjump.
So how do you deal with the fact that register is no longer a keyword?
Right. So the use of register in there is optional because of the ASM directive. The ASM directive takes care to put that variable in the register, so we don't need the register keyword.
Does that work without the register? The ASM work without the register?
Yes.
Okay.
Yeah.
I know it didn't on GCC.
It didn't?
At least last time I tried it.
Okay.
The register was mandatory.
Maybe.
And it was also illegal, which was a problem.
Okay, so to be frank, I didn't try. I just believe that ASM is the thing which puts it in the register. I thought register is not really honored by modern compilers.
It isn't, except if you put the ASM
Okay.
on GCC. I don't know what happens with Clang.
Okay.
I don't think I tried it, but the register was required in order to use ASF.
Okay, so this is like homework for me, like go and fix this up or look for alternatives. All right, thanks for bringing it. Moving on, there are a few other goals for LLVM's libc. We want the libc to be as modular as possible. Think of a new platform that is being brought up, or a platform on which LLVM's libc is being brought up afresh. As I said earlier in the talk, what exactly is a libc is determined by the platform maintainers. What they want to put in the libc is the libc for the platform. So if somebody is trying to bring up a libc for their new platform, we want them to look at LLVM's libc and pick and choose what they want to build the libc for their platform. So that is the kind of modularity we want to put in place for LLVM's libc. That modularity is largely driven by the build system, but it does have certain implications on the structuring and organization of the source code. So where it's relevant, I will point it out as to why things are the way they are and how it helps modularity. All right, so moving on to the core part of this talk, which is to talk about the challenges we faced and how we have overcome them. But before I actually talk about the challenges, obvious question could be, why should you care about the challenges at all? It's not often that a C++ programmer will wake up in the morning and decide to write a libc. And even if they decide to write a libc, how many would choose to implement it in C++? Maybe Rust, right? So as far as I know, only LLVM's libc is implemented in C++. And we have done this, as I have explained earlier in the talk, it was a very conscious choice to make use of certain powerful modern C++ features. But in general, for a general C++ programmer, I would think it's still a very interesting problem space. Some of the problems are really interesting and novel in the sense that it might kindle some kind of interest to make your head turn and take a look at it. But at a practical level, though, I still believe that some of the learnings we have, and I'm going to showcase some of them, that they can help in other areas where normal C++ programmers operate, like modernizing archaic coding practices, or even, I'm sure a lot of us have spent some part of our programming career in bridging old systems with new systems, right? So writing interfaces for new, interface layers between old legacy systems and modern systems. So the choice of using C++ actually puts us in that space. We are trying to provide a legacy, old C standard API using modern C++ practices. So let's see what kind of challenges we have faced and see how it can interest you. The general theme of challenges we have faced is with avoiding chicken and egg problems. So we have decided to use C++ as the programming language. But can we use the C++ standard library? Think about the modern C++ goodies like stdmove, stringview, span, and whatnot, right? So can we use them in the libc source code? Next interesting question is, can we depend on the C++ runtime? Think about features like virtual functions, dynamic base classes, virtual base classes, and exceptions. They all are facilitated by the C++ runtime. So can this libc depend on the C++ runtime? The last question I have on the slide is, can this libc use C++ features which themselves require runtime support from the libc? Right? So do you see the chicken and egg problem emerging in all of these questions, right? So I will take up each of these questions individually and provide how we viewed them and also explain the solutions, try to justify the solutions we have put in place to answer these questions. So for the first question, can we use the C++ standard library? Let's look at how the two most popular C++ standard libraries, libc++ and libstdc++, are built today. They assume the existence of a fully functional C standard library. They include the C standard headers. They call into the C runtime. That is the implementation of the C standard API. So can we really use the C standard library then in building this libc? We are building a libc using another entity which assumes that the libc already exists. So do you see the chicken and egg problem here? So can we really use the C standard library to build the build LLVM's libc? Let's see what we did. There's another angle to this question. So we want LLVM's libc to be usable on platforms where the C++ standard library is not yet available. Again, think about platforms which are just being brought up. One of the first toolchain components you will bring up for such platforms are a cross-compiler. Right? Once the cross-compiler is working, you'll try to bring up the libc for that platform. So when you bring up the libc, very likely the C++ standard library is not yet brought up or not yet available. So we want the libc to be usable in those contexts also. So can we really use the C++ standard library? Well, the answer is a constraint that we have imposed on ourselves, that we cannot use the C++ standard library. Maybe in future, when we are able to, in near future, when we are able to use more modern C++ versions and more modern compilers, we can use the freestanding C++ headers and make use of the goodies like string view, array, span, move, and whatnot. But the consequence of imposing this constraint on ourselves is that can we make the libc source code look like modern idiomatic C++? A large part of modern idiomatic C++ is driven by the use of the C++ standard library. If we rule out the C++ standard library, so what are we setting ourselves up for? So why are we using C++ at all, right? So the answer to this is an anti-pattern. It could be atrocious, come across as atrocious for some of you, but here it is. This is what we did. We implemented a self-contained C++ standard library within the libc. Now, the caveat is that this is not as wide, as exhaustive, or as featureful as a normal C++ standard library. It has been implemented on an as-needed basis, and we have just the functionality and features necessary for the libc to work, right? To distinguish that these goodies come from the libc's C++ standard library, we have put all these classes in the CPP namespace as opposed to the STD namespace. Even if we use the STD namespace, it wouldn't be much of a conflict because all of our code is within the namespace __ LLVM libc. But for the developers, to avoid any sort of confusion, we have used a new namespace called CPP. Now, with these features available, we are now able to use more modern practices in building this libc source code. So what I have here is a table of what used to be.
So how is CPP byte defined? Because that's a special case. Std byte is a special case in the standard.
Yeah, so we have just type defed it to uint8.
Okay.
All right, so with that self-contained C++, self-contained replacements for the C++ standard library features available, we are now able to use more modern ways of constructing our internal interfaces and APIs. For example, on the right are the old patterns that are typically used in building a libc versus the new patterns that we use in our libc. Instead of passing a const char pointer and a sized argument, we just pass string v values and return values. Instead of a raw pointer and size arguments, we use span. If you look at the specification of many C standard functions, they return a special value like null pointer or -1 or 0, depending on the context, on error, but return a normal value otherwise. So instead of using that pattern, we use optional as a return value. Likewise, if you go and look at few other C standard function specifications of C standard functions, they set the errno on error. We don't do that in our internal interfaces. We use the expected return value. And then I have also reinterpret cast versus bit cast. It could be a bit surprising, but then we had to do this comparison because we had to get around the problem we faced with strict aliasing of modern C++. The last item, returning using pointer arguments versus returning a value of a focus type. So if you again go back to some of the functions in the C standard library, you will notice that many functions take input pointer arguments into which the function writes an output value. And for us, that's an anti-pattern in C++. So we have chosen to craft a focus type and return that type instead of writing output values into input pointer arguments. All right, so what I have here is the implementation of the getEnd function. It's fairly straightforward code, nothing special over here. I have it on this slide just to show how we use the power of string view. We do all string manipulation using the string view API instead of dealing with raw pointers and sizes. It's essentially used to parse and analyze the strings corresponding to environment variables. Well, this is another example where we use string view as an argument as opposed to passing const char pointer and a size argument. So this is the internal abstraction by name write to stdr. All platforms which support LLVM's libc have to implement this. All they have to do is take a message and write it to the standard error stream. What I have on the screen here is the Linux implementation, which is essentially making a syscall. As you can see, it is taking the string view argument and extracting the raw pointer and size arguments and making the syscall. All right, so I had said earlier that many C standard functions set errno on error, and they also return a special value on error. So what I have here on the screen is the spec for 3 dirent.h functions as specified by the POSIX standard. I also have, So I also have the wording in the POSIX standard, which talks about what happens when the function hits an error. They all say that on error, errno is set. And they also say that the first 2 functions, openDir and readDir, say that they return a null pointer on error, and closeDir says that it returns -1 on error. So the pattern, you can see the pattern. All of them return a special value on error and set errno. The internal abstraction we use to implement this POSIX dirent API is to use more modern ways of constructing APIs. For example, the open function is a static function which returns an error R. Likewise, read returns an error R. This error R is nothing but type sugar over expected. The unexpected value is of integer type because errors are to be stored in errno, and errno is an int type variable. So our unexpected type is of an int type. The last function, the close function, is a bit interesting. Interesting because I didn't change the function header in any way. I mean the function prototype in any way. All right, it takes a dir star pointer, because it's a freestanding function, whereas this is a method. So it is effectively taking the this pointer as the first argument, which is the dir star again. So it is the same. So what's modern about it? What's modern about it? I don't think there's anything modern about it, but I have it here just for the sake of completeness. If you go back to the standards wording, it says -1 shall be returned on error, right? So, but error is set to indicate the error. So what should be returned otherwise is a non-negative value. So what we have chosen to do is to return the error value always. If it is 0, that means it is success. No, it's not really an error, but still error. It's a valid value for error. So we are essentially returning the error value from the close function.
That doesn't seem correct. If a previous API had failed out and set the error no, that value would still be left in the error no. And then if yours succeeded, you do not set it as 0. So therefore, you're returning a previous error.
Right. So let me go to the next slide. That should probably clarify that point.
Okay.
So this is the internal interface, right? This is the API or the interfaces we have in the internals of the libc. What happens, or where exactly the error is set, is in the public function. This is the implementation of the public POSIX open dir function. So this is where we set error. We have a pointer now. Right. You see libc error equal to dir.error. So on error, this is where we set error in the public function. So we are trying to set error just in time when we return from the public function and not in the internals. Internals are all error agnostic. They don't know about error. They don't touch error.
Okay.
Does that answer your question?
Yeah, so I've done API wrapping like this before also
Okay.
for sockets.
Okay.
We had to do the same thing.
All right, so moving on. Yeah, going to an example of bitcast. So I have two snippets here, one on the left and one on the right. So one on the left was what we used to have, and we switched to using bitcast a year ago. The reason we did it was that, well, so before I talk about the reason why we did the switch, let me briefly explain what's going on here in the code. So FP bits is a class which is encapsulating the bits of a floating point number as an integer. So essentially we are casting floating point bits to integer bits or integer bits to floating point bits. So you have the get val, which is casting the integer to floating point, and you have set val, which is casting the floating point to integer. So if we use reinterpret cast, it is violation of strict aliasing rules because float and integer types are not compatible types. And so we had to use bitcast. And bitcast is coming from our implementation of the C++ standard library, which uses the built-in bitcast when available or does memcopy. Memcopy is what is mandated by the standard, that bitcast should be doing memcopy, sorry. The good part is that when you have memcopy of small types like integer to floating point or floating point to integer, compilers optimize them out with emit codegen to native instructions which do them in one instruction instead of actually calling the memcopy function. So if you go back to the table I had, this one, the last item here was about using a focus type as return value instead of using input pointer arguments to get output values from functions. So I have an example of that. So for that, to make the case for that, let's look at the standard specification for string to integer conversion functions. If you see, all of these conversion functions take an input argument, which is the pointer, the end pointer, right? So the standard expects that after the conversion of the input string to integer, the function writes the pointer to the character after the integer part in the input string into this end pointer. The exact wording of the standard is as follows. A pointer to the final string is stored in the object pointed to by end pointer, right? But the standard also has a couple of other things, a bit vague and ambiguous in my opinion, because the standard says if no conversion could be performed, 0 is returned. But 0 is also a valid conversion value. So the standard doesn't have any way to distinguish between an error 0 and the correct successful 0. But the standard has provision to flag overflows. So it says that if the input string cannot fit into the target integer type, then one of the extremum values should be returned, and error should be set to eRange. So internally, instead of mimicking this API, what we have done is make use of templates. We have one function which handles all string to integer conversion. And we don't write output values into input pointer argument. Instead, we use a focus type called string to number result. And this is a simple struct, again a template. It holds the correct conversion value in the field value. If there was an error, then it will hold the error value in the field error. And instead of returning the pointer to the character after the integer part, it returns the number of characters consumed to produce or to perform the conversion from string to integer. So this interface is used by the public functions, much like the direct API, right? Just in time, when the error is detected, error is set, but otherwise, the end pointer is set according to using the parsed length field of the stir to num result. All right. So all that was for the constraint of not being able to use the C++ standard library. Now let's move on to the next constraint, which is to not use the C++ runtime also, to not use any features which add a dependence on the C++ runtime, which means that we can't use the virtual keyword anywhere. No virtual functions, no virtual interface. Sorry, virtual inheritance. Why do we want to disallow the virtual keyword? All virtual related mechanics are implementation defined. The C++ runtime facilitates the operation, the runtime operation of these virtual mechanics. So by using virtual keyword, we are adding a dependence on the C++ runtime, again, creating that chicken and egg problem. So we completely disallow the virtual keyword. Not just the virtual keyword, we disallow using any C++ runtime feature, which means we can't use new and delete also. So what do we do about allocations and deallocations? We want the source code to look like that of a normal C++ library, but we are saying you can't use new and delete. So what do? So what about abstract interfaces? Virtual functions are a way to do type erasure plus provide abstract interfaces. So if you don't have virtual functions, how do you do abstract interfaces? Like before, I will take these questions up separately. We don't have a great answer for the abstract interfaces problem, but I will touch upon that later at the end of this talk. But let's look at what we do about allocations and deallocations. Well, again, the goal is for the source code to look like that of a normal and modern C++ library. As I said, we cannot use new and delete from the C++ runtime. So what do? We provide our own overrides for new and delete. But there are lots of caveats here. We cannot just override new, because if we override new, we cannot just override new and delete, because if we do override with out-of-line implementations for new and delete, we'll be replacing new and delete for the applications, or any application that links to this libc will get new and delete from the C runtime as opposed to from the C++ runtime. And we don't want that to happen. So we want to use new and delete, but we want this new and delete to be applicable only to the libc code. So let's see what we did. So we use this C++ 17 feature of user-defined placement new. So all it does is it allows us to add another argument to the operator new function, right? As you can see on the slide, it takes another argument by name Alex Checker, of type Alex Checker, sorry. and the actual allocation is delegated to this alloc checker. So let's see what this alloc checker is. It's making a call to a static member function of alloc checker, right? So the static function alloc is nothing but a function which is calling malloc internally. Over and about allocating memory with malloc, it also has few convenient conversion functions to bool, for example. So how do we use this alloc checker and this new operator new? This way. So we first instantiate an alloc checker instance, and call operator new as if we were doing a placement new, but instead of giving it memory to place the type into, we give this alloc checker instance. And so what this ensures is that we are not breaking new for other users. This new is completely libc internal and libc specific. It doesn't collide with any other operator new that users might themselves provide and override. And it also has a very nice way to check for allocation failures. You can, of course, check whether the return value is null pointer or not, but then using the alloc checker itself has few other nice features. I'm not going to go into them now because it's going to just drag this slide a bit too much. So the essential point I'm trying to make here is that we have implemented a special user-defined placement operator new to be used by the libc internal code. Likewise, we've also implemented a special operator delete. Now, operator delete is even harder because there is nothing like user-defined placement operator new. So what do we do about it? You can't do an inline implementation because standards disallow inline implementation of operator delete. So it has to be out of line. But this out of line.
So wouldn't another approach to that be to have a function that calls an explicit destructor and then calls the operator delete explicitly?
Function that calls an explicit destructor.
Because the reason you use new is that's the only way to call a constructor explicitly.
Right. Mm-hmm.
So normally when you use placement, you have to have the typical way to use, because there's no corresponding way to call a placement delete.
Right, yes.
So
mm-hmm.
that's the core problem.
Right,
but
yes.
The way you typically get around that is to call an explicit destructor followed by deallocation.
Right, so we do a mixture of that. So let me show what we do with operator delete itself, like without using any special function to call it, make an explicit call to the destructor. So what we do is we actually do implement operator delete out of line like any other normal operator delete function. But in the declaration, we add another ASM magic. This ASM magic, what it does is replaces this operator delete in the generated object file. The linkage name for this operator delete function is what you specify there. Right, so that is a special libc internal, libc specific delete operator. And so when you compile the implementation, the .cpp file, which includes the .h file, the resulting object file will have a delete operator with the name __ LLVM libc _ delete. But when you call the delete operator, for example, I have an example here. So this is how you would normally call the delete operator, right, on any object which is allocated using new. Now, to get the special delete operator, you need to include the new.h, which is internal to libc. So you include the new.h so that the compiler knows that the linkage name for the delete operator there is not the standard delete operator, but it is a special delete operator with a special name of __ LLVM _ libc _ delete. So this is again an anti-pattern. I don't think anybody should do it, right? But being a libc, we have the liberty to employ these anti-patterns and get our work done. All right, so that was about allocations and deallocations using new and delete like one would normally do in a normal C++ library. Moving on, the last item I had in the list of chicken and egg problems was, can we use features, C++ features, which themselves require support from the C++, from the C runtime? And the answer is no again, because it is yet another chicken and egg problem. And I'll explain how it actually does become a chicken and egg problem in this case. But the consequence is that we can't use any global objects which require initialization and destruction at runtime, which is, so think about the @exit callbacks, right? So when a user registers @exit callbacks, you typically, or you would ideally want to store them in maybe a vector, a global vector. And so if you use a vector to store these @exit callbacks, the global vector has to be constructed at program startup time, which means that typically a vector allocates memory in the constructor, which means that it's making a call to malloc. But the implementation of malloc itself typically uses global state, global objects. So now you see the chicken and egg problem. Which has to come first? Should the @exit callbacks be constructed first, or should the malloc global objects be constructed first? It's a big chicken and egg problem, big mess. And we have an additional goal for the LLVM libc project that the user should be able to provide their own allocator. So if we had just one allocator to deal with, our own, an allocator which we control fully, maybe we can still manage that. But if we want any allocator to work with the libc, it's not possible to handle it in a clean way. So what we do is to disallow global objects which require runtime initialization or destruction. So what does that mean? How do we disallow? We want all classes of global objects to have trivial and defaulted constructors and destructors. Well, it need not be trivial constructor, but it has to be trivial destructor. So that's why I don't have destructor here. So it has to be a trivial constructor, and that constructor should be a const expression. Where do we use this? Before I go to an example of where we use this, let's talk about the destructors also. Now, likewise, you don't want the destructors themselves to be depending on the C runtime to invoke them. So you don't want any destructors in your in the classes from which global objects are instantiated. So what happens is that what we do is that, like you have pointed out, we use an explicit function to do the cleanup here. We can't expect that the destructor be called and the cleanup happens automatically, because it leads to the chicken and egg problem again. As an example, I have the same @exit callback example. So instead of using a vector, we use a data structure called block store. So what this block store is, in comparison to the vector data structure, is that it starts off with a block of memory. It doesn't allocate memory to begin with in the constructor. It just starts off with a block of memory. And when more memory is needed, it allocates another chunk of memory instead of moving the existing vector to a larger chunk of memory. Right? It allocates a new chunk of memory and makes a linked list of these chunks of memory. And that's why it's named block store. The advantage is that constructor doesn't have to do anything. It's a no-op constructor. There is no overhead, runtime overhead, because of the linked list added in, because typically you only, with respect to @exit functions, you go over them in order. And so the linked list overhead is minimal, that we don't have to worry about.
So I'm not quite sure why vector can't have a const x for constructor, because wouldn't it just initialize all the pointers to null?
Yeah, that is correct, but that's not how the standard specified vectors operate, the standard vectors operate. So you're saying that all of them can be null, and when an element has to be added to the vector, like push back to the vector, then you allocate, right? That is possible. That's one solution. But why start with null? Why don't you just start with a chunk of memory, right? And that's what we do. We start with a chunk of memory instead of a null pointer. Does that answer your question? Or does it seem convincing enough?
Well, I mean, that is something that works.
Yeah, either of them works, but we have chosen this approach. But we have not, to be frank, we have not compared like what happens if you start with a 0 or like a null pointer in the
I'm pretty sure that's what I've seen in vector implementations.
Okay.
If I recall correctly, isn't std vector in recent C++ standard versions const expr? Are they constructible as const expr yet? I recall that was a proposal at one point.
I think so, but don't quote me on that. I haven't.
Well, yeah, I mean, I don't know about standard vector though, yeah, so I'm not sure. Yeah, that's another homework that I can do. I can go look up what exactly is the latest specification for vector. But no, this is doing something equivalent. So we called it block store. We invented this 2 years back when we were just feeling what exactly is this libc about. So yeah, this is an approach we have taken to start with the block of memory instead of starting with a constructor which allocates memory. So as I have explained earlier, the constructor is the const expression and defaulted. The destructor is defaulted. And we use an explicit function, a static method by name destroy, to go and clean up the resources used by the block store. So how is it used? This is how we do run through the at-exit callbacks. The while loop is doing the handling, making the calls to the at-exit callbacks. But at the end of it, we make the call to that explicit destroy function to clean up all the at-exit callbacks or clean up the data structure. All right, so what I discussed so far was about the chicken and egg problems which we have faced. Next, I will move on to items which are not really chicken and egg, but which use the power of modern C++ features to do something really cool in comparison to the other implementations from other existing libcs. So I will take the example of compile time tables used by the implementation of stir error function. To recollect, stir error function is a function which takes an error number and returns a string, a human readable string, explaining what that error is about. It's not a very big description. It's a small phrase like success or out of memory or something like that. At a high level, most libcs do implement this as table lookup. Given the error, they go and look up the table to find the right string and return that string. In LLVM libc also, we do the same thing. But what is different between LLVM's libc's approach versus other libcs is that we do the construction of this table all in C++ using the power of const expressions. Other libcs do the same thing using really complicated preprocessor macro magic, which almost is impossible to read if you are not the one who wrote that. Let's see how we do it. So to begin with, we handwrite certain tables. So you can see here is a table of errors specified by the C standard. There are 4 errors. One of them is success. The other are edom, erange, and elseek. The point to note here is that other than the 0 value, edom, erange, elseek, those values are not specified by the standard. They are determined by the operating system ABI. So if you are on Linux, for example, they have Linux-specific values. And in Linux, they don't have values 1, 2, and 3. So those values are not linear. If you actually put the messages in an array with the error numbers as indices, then it's a really sparse array. Likewise, we have another table, a hand-constructed table for POSIX errors. None of the error numbers are in order. Maybe some of them are, but they're just happenstance It's not by design. So I have used two types in these tables. Like one is message table and the other is message mapping. So let's see what these types are. So message mapping is a simple pair holding a number and is associated string view for the message. Message table is type sugar for an array of message message mapping instances. So how does this all come together? So given any platform, this is how we construct the platform errors. So for Linux, for example, we just add the C standard errors, the POSIX errors, and the Linux errors to get the full list of Linux platform errors. We don't have any other platform supported, and that's why we have just an else class with platform errors equal to the C standard errors. But if you note, it's a const expression. And we use the operator plus. So how is this operator plus implemented? This is yet another const expression. It is just taking two arrays and returning another array, all being done at compile time. So how do we use these tables in implementing stirrer? First, we have three more const expressions. Const expression variables this time. One of them is initialized by a function call to a function named total stirlen. So what this total stirlen is doing is that, remember, these tables are an array of message mapping instances, and each of them have a string view element in them. So what it essentially is doing is, it is going over all of the strings and adding up their lengths. It is including the null terminator for each of those strings in calculating the total string length. Likewise, max keyval, what is it doing is that it is going over all of the platform errors and identifying the maximum error value for that platform. And how are they used? They are used to instantiate yet another const expression variable of type message mapper. And you see, message mapper takes two template arguments, the total stirlen and error array size. Let's see how message mapper is defined. So message mapper has two members. One is the message offsets and other is a string array. So instead of going over the code, I will verbally explain what exactly is going on here. So this total stirlen is calculating the full, if all of the strings were arranged next to each other, what would be the size of the full chunk of memory? And that is what total stirlen is giving you. And this error array size is calculating is representing the maximum error used for the platform. And so in the message mapper, we have an array called message offsets of array size, right? So this is where we have offsets stored for each error number. So given an error number, say E range, we look up at what offset is this string residing in the string array and go and return its pointer when we have to get the corresponding string error message for the error number. The getString method does that. Now all this magic is happening in yet another const expression constructor of message mapper. I've split it in two different slides because it's a fairly big function. And the beauty is that all of this is being evaluated at compile time. It follows here. So the first part of the constructor is here, and the next part is here. So all it is doing is that it is taking the error messages from the platform errors table and putting them all together in one big chunk of memory. Right? And it is all being done in compile time. So the nested for loop is where the copying is happening. The string is being copied from the platform errors table into this message mappers table. So the beauty of all of this is that when you actually compile this, none of this ends up in the object file. When I say none of this, I mean these tables, the stdc errors, the POSIX errors table, even the platform errors table, none of them end up in the object file. Likewise, the operator code for operator plus, the code which is evaluating the total Sterland and max key val is not there. All you have in the object file is the final table of errors, the one highlighted here, the one with 3,652 bytes. Right? All of the tables are gone. So this is on Linux. So it's including the stdc errors, POSIX errors, and Linux errors. And you don't see those tables. This is the dump I got from readelf, using readelf. And you see this, except for that table, no other object is there in this file. So what have we achieved? We achieved the same functionality that other libcs have achieved using macro magic, really complicated macro magic. But we have used really simple, straightforward C++. Listing of an array of errors and corresponding messages, and putting them together using the plus operator, and then a constructor which arranges those messages into one big chunk of memory. All of this was achieved using const expressions, and in the end, everything is gone. Only this is there in the object file. So the reason I have used this as an example is because it is, in my opinion, the best example to illustrate the power of const expressions and why C++ is still worth it for LLVM libc as opposed to using just C, pure C. Well, there is a talk later today at 4:30. Let me just look up. It is titled "Compile Time is the New Const Expression" by Daniel Withoff at the Flug Auditorium. That would be really interesting in the context of all of this that I've presented here. So I'm going to go, if anyone's interested, feel free to go attend the talk. Moving on though, with this talk, so I have shown like the most complicated example of using a modern C++ feature, which is using const expressions where possible, and getting the benefit of compile time tables without using complicated preprocessor macros. Now, I have an example, a very straightforward example of how we use templates to avoid duplicated code in the math library. If you look at code from other libc implementations, they have duplicated code for functions like. Okay, before I talk about other implementations, let me talk about how the math library is actually, right? So if you take any math library function, say the sine function, there is a float version, there is a double version, and a long double version. There is sine f, sine, and sine L. So likewise, there's another function called log b, and there's a log bf function, log b function, and log bl function. So if you go look up other libcs, they'll have different implementations for each of these functions in different .c files. What we have done is, where possible, and when I say where possible, I'll explain that a little later, but if I take the example of this log b function, we have one single template implementation for this function. We have not used any magic numbers. We have all symbolic references to numbers or whatever that's relevant for the implementation of this function. So if you go look at, I don't want to name a libc, but if you want to go look at, say, glibc, for example, you will see that the implementation of log b is peppered with magic numbers. We don't have any of those magic numbers. It's pure, straightforward C implementation. Sorry, C++ implementation. All right. So another powerful feature that we use in the math library is variadic templates. What I have here is an example of polynomial evaluation. This is a template implementation of what is referred to as the Horner's formula to do polynomial evaluation. If you notice, it is a recursive call, but the beauty is that you can do an FMA operation to perform the final evaluation of the polynomial. And so I don't know how to do this exact thing without using variadic templates. Maybe macros, but really complicated macros. I don't know, but this is what using variadic templates gives us. All right, so I have presented the challenges, the chicken and egg problems, how we overcome the chicken and egg problems, and some of the other cool things that we have used, like const expression, the const expression magic to generate compile time tables. In my opinion, const expressions is one of the underused and poorly understood feature of C++. And there's a reason for that. The reason is that if you Google for it, there are many articles which say, don't const expression everything. There is a talk from CppNow 2021 with title, don't do const expression for everything. But then we take the anti-pattern approach in the libc, just because we can. And we were able to pull off some really cool stuff, like the construction of compile time tables as opposed to using macro magic. Right, so what's coming in future? More const expressions. More const expressions because they have more power, and we feel that we have not yet tapped into the full power of const expressions. This time I'll talk about an area where const expressions don't play well with, and that is compiler built-ins. So take, for example, the compiler built-in named add with carry, like built-in add CB, add with carry byte, add with carry, not byte maybe? Yeah, byte, add with carry short, and add with carry long, 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 whatever. So the thing is that these compiler built-ins are not const expression functions. There is a reason why they're not const expression functions, because they are compiler built-ins. They're supposed to be emitting specialized instructions for the target architecture. And so the compiler, the front end, the C++ front end, doesn't really know what those built-ins are doing. It is for the back end of the compiler. And so const expressions don't play well with compiler built-ins. Now, is that a problem? Yes, it is a problem. It is a problem when the const expression isn't evaluated at compile time. If it is evaluated at compile time, we don't really need the compiler built-ins, right? It's evaluated at compile time. We don't need any specialized instructions to evaluate anything in the const expression function. But if the const expression function is not evaluated at compile time, and since we cannot use built-ins, we end up with a poorer implementation. So the current solution we have taken is a very hacky. What we have done is to provide R-value overloads to functions and methods which operate on R-value overloads for const expression functions and methods. An example is this. So we have an internal type called uint. It can be as big as possible. It can be 128 bits. It can be 256 bits, whatnot. It's used by the internals of math implementations. We have this operator plus, right? And then which is not a const expression, but we also have an operator plus, which is a const expression. And notice the difference. Apart from not being a const expression, that is taking a const reference argument, whereas the const expression flavor is taking a R-value reference argument. Now, they're also making different function calls. One of them is calling add with carry, and the other is calling add with carry const. If you go into what exactly they are, oops, I missed this slide. Anyway, I'll talk about that. So if you go into what this add with carry is essentially a template function which is invoking the built-in add with carry function named built-in add CB or built-in add CS or whatever that's relevant for the types, right? Because that is not a const expression, because the built-ins are not a const expression, we cannot call add with carry from the const expression flavor. And so the normal operator plus, which takes a normal const reference, is not a const expression. whereas the one which takes R value reference is a constant expression that allows us to do something like uint a value A plus a literal value. When you have a literal value, I missed adding the slide, but I hope you're getting my point. So when you're adding two literal uint values, you want the second one to kick in because you want it to be evaluated at compile time and not at runtime using the const and flavor. The disadvantage, though, is that if somebody did a uint var A plus std move uint var B, still the second one will be called, and it will get the poorer add with carry const, which doesn't call the compiler built-ins. And that is the problem. We just started doing this. We still have to go see how it is affecting the performance of other parts of the libc. It's essentially used in math implementations and, if I remember right, string to floating point and floating point to string conversion functions. We have not yet done the performance analysis as to what happens because of this, but this is something we started doing, and we hope that in future, like in the very near future, we'll be able to find some better solution to use the power of constant expression when possible, otherwise use the power of compiler built-ins.
Question.
Yep.
Did you consider the use of is constant evaluated so that when a constant expert function is not able to be evaluated at compile time, the blocks of code that do make use of compiler built-ins is protected by the is constant evaluated check, or was that not an option available to you yet?
So our primary use case was adding two literal values, adding two literal uint values, right? So how do we apply is const evaluated in that context?
My understanding is that the reason for this bifurcation of runtime evaluated versus compile time evaluated overloads, as I understood your explanation, was that we cannot use built-ins in the const expert in the compile time overload. But my understanding is that the is constant evaluated feature in C++20 is specifically designed for this purpose of when a const expert function does not is not either negated or not. If it is able to be evaluated at compile time, use compile time code. If it is not able to be evaluated at compile time, fall back to runtime appropriate code blocks.
Oh, so you mean we could use some kind of SVNA over these two different overloads and pick the right one at compile time?
No, in your implementation of AppWithCar, you just say, if is constant evaluated, do the const expert version, otherwise else do the runtime version.
Oh, okay. Okay.
Which would then make this non-const expert, which means he couldn't use it in all of his
No,
spots.
it is const expert though.
It is a const expert function that selects certain different code paths depending on whether it is constant evaluated or not. And so you can still, you should in theory still be able to make use of runtime only, like can only be used at runtime constructs in the protected code paths when the const expert function does not happen to.
Yeah, I see what you're saying. I think we could do that. We could do that here.
Okay.
So you're saying that we could use the const expression if, along with
Do not use const expert with
Yeah,
constant
there's a
evaluated.
very well-known footgun regarding the use of if const expert with is constant evaluated, but I'm pretty sure there is a correct solution.
Yes,
that
just
Okay.
the normal if.
Yes.
Okay. Yeah, so I should go and explore that. Yeah. So if we, yep, that's another homework. Thanks for bringing it up. Like it's another thing it's another point for me to go do homework on. Yeah. Thanks for that again. And moving on, one of the other things that we want to explore is the use of concepts to formalize some of the internal abstractions we have. Today, because we can't use virtual functions, we use the poor man's virtual function mechanism, which is to pass around function pointers, which isn't really nice because once you start passing around function pointers, there's no limit. You'll start thinking like, okay, we did function pointer there, so why can't we do function pointer here? And then you'll see that the entire code base is peppered with function pointers. So we want to take control of that situation by using some kind of concepts plus CPP function magic. CPP function essentially because it can do some kind of type erasure, which virtual functions do, and which also function pointers do. So we are hoping that a combination of concepts and CPP function will help us put together a better solution for dealing with formal abstract interfaces internal to the libc. One example where we have a formal interface is the file abstraction. So we have a file abstraction, and each platform has to implement its own, specialization of that file abstraction. So with virtual functions, all you do is inherit, you subclass that file base abstraction, and then you're good. But without virtual functions, you need to have other magic. So what we currently do is we have function pointers for every method in the file abstraction. So it's not a great situation.
You could always basically do what virtual functions do and create a struct that has all your function pointers that have a pointer to it.
Right. So that's what we do essentially. But that's the poor man's vtable that I was talking about.
That is exactly how it's implemented.
Right. Yeah. But it's not great with respect to code cleanliness.
I mean, you can make templates to generate that kind of code for you.
Yes, that is something we already do, actually. We use templates to generate that code. It's still function pointers. You still have to, the platform's specialization has to set up the function pointers and pass that struct to the base class so that the base class thinks that it is now an incarnation of that specialization for the platform. With this, I come to the end of this talk. Thanks a lot for joining. I did finish 15-20 minutes before my allotted time. If you have any questions, feel free to shoot and show me things which I have missed or things which we can improve. Thank you.
I have a small question on the slide where you were showing the offset indices for error messages. Was your choice of using the int type for the offset index deliberate? If so, why?
Yes, so it was deliberate because they represent the error numbers. The error numbers have to be stored in the error variable, which is of int type.
Oh, so the error no value is doubling as an index
Yes,
into the message table.
yes.
Okay, understood.
Wait,
That's an old
but
BSD thing.
Okay.
Are you talking about the
Right there, yes.
that one? Okay, that one. It need not be integer type. Okay, so we use this special -1 value, and that's the reason why it's int. The error numbers need not be contiguous. As I said, when you construct the array of, when you construct the table, that is not a fully populated table. There are values which don't have corresponding messages. So this -1 is there to indicate that there's no corresponding message for that error number. So that's the reason why we use this int value, to flag that there is no error message associated with that error number.
There's about 12 different versions of error number systems. BSD has one, Linux has one, Unix has one, sockets have one. Some of the times the errors correspond, many times they don't.
Right.
And there are big gaps in them. They try to inherit from each other, but it doesn't work. And some don't apply to cross systems. Yeah. So it's just going to always been int, even though it's sloppy. That's why you can, when you go to do a socket, you go to read, it always returns an int, because it actually could be an error code coming back. Normally you can always, when you go to read something, by definition, you can't read a negative number of bytes.
Right.
But
As C++ code, however, it just flagged an alarm to be using a -1 value instead, as opposed to perhaps like an optional. If there is no corresponding value, then why not an optional? Was it too much overhead or some other factors?
Well, to be honest, it wasn't considered at the time when we wrote it. We were like too glad that we got this working. Like, you know, we wrote all of this code, and when we looked at the object file, we only saw one object. Everything was just wiped out by the compiler and the linker. That was really awesome, in my opinion. So we didn't really. So to be fair, I think we should do a take 2 of all of this to go and clean up. This is all take 1 that I'm presenting. But yeah, I take your point. If there's STD optional, I think we could use that over there. Yep.
If you go back to the slide where you call the internally defined view and delete, there's a check around or after the allocation. Yeah, so in the if statement here, checking if not AC. I wonder if this is supposed to be a check on the object itself.
They're equivalent at some level, but then what Alex Checker does is that in our take 1, it is not yet fully featureful, but we plan to extend it to flag, at least in debug builds, crash or do something, fire an assert or something, if Alex Checker is being used for more than one allocation. If somebody wants to use this for more than one allocation, they should reset or do something of that sort. So they can't use the same Alex Checker for 2 different new operations, right? So what we want to enforce the policy of using the Alex Checker to look for allocation failures, because that is where we can catch the reuse of Alex Checker. Does that make sense?
Yeah.
When you're saying reuse, re-entrant?
No.
Or because it's thread safe or stack safe because it's a local, right?
So you could have another new call to another call to the new operator using the same Alex Checker.
Well, either it would be going a constructor would be calling a new again, or they're just sequential. If they're sequential, they're 2 separate blocks.
It is the same Alex Checker, right? So
Yeah.
this Alex Checker is essentially storing the state for the previous allocation. And so if you do another allocation without rearming or disarming the Alex Checker, something should fire and tell you that you're
This is
missing.
just a glorified out param.
Glorified out param. Out param is in?
I mean, is a parameter to a function where you're expecting a return value.
Yeah, yes, it is. Essentially that, yes.
Capable of storing more information than just a null pointer on
Yeah.
failure.
Right.
Mm-hmm.
Just to confirm, is that overload of operator new no except? It will not throw?
Yes, no except,
Okay,
yes.
just confirming.
I think I do have it in my, yeah, no
Okay,
except.
there we go.
Yeah. Mhm. Anything else? All right. If not, I'm happy to take more questions outside. Thanks for coming, and thanks for actually pointing out a few things which can be done better. Until next time, bye-bye.